Christophe very nicely explained what we expect from the theory, and so now I will discuss a bit more what observationally we can measure about this connection between galaxies and the cosmic web. So just as a quick introduction, what you see here is a 3D rendering of a small part of the horizon AGN volume, color-coded in background by density, and you have here the filament from so extracted by the dispersed skeleton in white, and you see also this velocity field line here, color-coded by vorticity. And on top of that, I have added the dark matter halo from the simulation. So we expect that, well, first where the halo form, and then the accretion rate onto this halo will depend from the large-scale environment, from the tide driven by this large-scale environment. And in addition, we also expect that the properties of the gas, like the thermodynamics and the dynamics of the gas, depends on the location within this large-scale structure, and therefore, as accreted onto the galaxy, will further shape the galaxy properties. And the point that I would like to make first is that looking at the connection between galaxies and the cosmic web can give us a further constraint on the galaxy formation model. So how do we do in simulation currently to reproduce galaxy population, and so where we are in terms of galaxy formation model? So well, all simulators will tell us that their simulation is broadly in agreement with observation, and that's true when we consider the overall population and some global statistics like the stellar mass function, or maybe the main sequence, or how stellar mass and star formation relate. However, if we look into the details, for example, at the tail of the galaxy population, like the quenching population, which is basically the tail in terms of star formation rate, well, we see that simulations are in disagreement between each other and also between with observations. Just to illustrate this, what I show here is the stellar to halo mass relation. The gray area here is as measured in observation by jointly fitting the galaxy mass function and the two-point clustering and the two-point correlation function. So the gray here is observation, and I have overplotted different simulations on top of that. And while you see that the overall shape is more or less reproduced, well, either the normalization, so the normalization is not always good. And also, if we look in massive halo, it's very clear that all simulations overpredict the stellar mass formed in the massive halo. So although the shape is broadly reproduced, you see this kind of disagreement. If I look at another very simple statistic, which is the main sequence, so star formation rate as a function of stellar mass, we see that all simulations show more or less the same main sequence. However, if we look at galaxies below the main sequence, so more or less the passive galaxy population, we see that those galaxies, they occupy a different position in this 2D plane, depending on the simulation. And also, if we look at the fraction of passive galaxies as a function of stellar mass, as compared to observation, which is in gray, well, you see that the simulations do not do very well. So there is really something which does not, is not really well reproduced in terms of processes which drive this quenching population. So now, beside the quenching, it should be noted that also this cosmological simulation lack of strong starburst galaxies at very high redshift, which is an additional indication that maybe quenching do not occur at the right moment or in the right mass range or other galaxy properties range. So what I would like to say now is that if we measure the spatial distribution of quenching within the cosmic web, we could put additional constraint on the physical processes driving this mechanism, either because quenching might genuinely depend on the cosmic web environment or on the environment, or or because looking at how the physical processes, like for example feedback, which can drive quenching, so how these processes conspire with the environment to drive the observed population can give us new constraints and can help us to understand them. And in addition, it's quite important to go towards higher redshift because this is where the discrepancy between simulation and observation is the more prominent. So observationally, we have already some evidences that there is an impact of cosmic wave on some galaxy properties. Just to illustrate it here, what I show here is a measurement that we did in 2018, but it was done by other teams as well. And we measured the distance of galaxies as classified as passive or star-forming to their nearest filament. And this is in a quite narrow mass range. So what we see here, so it is, what is plotted is the PDF of these distances in log scale. And basically what we see is that there is a slight tendency for passive galaxies to be closer to their filament than star-forming one. And this is seen in terms of passive versus star-forming population, but also in terms of metallicity or gas content. Obviously, this trend is quite subtle. It's not very, I mean, it's not very significant. But because it was found in different surveys, there is an indication that this could be real. As we heard from Christophe, this could be driven first because of the tidal field, which shaped the accretion rate onto the halo, so we can induce delay on the accretion. This can also be a simple effect of density. Halos in denser environment will collapse first, so galaxies in this halo will have got more time to become passive. And it's quite difficult at this stage to disentangle between the effect of density and effect of proximity to filament. And in addition, the filament definition varies from one study to the other, so we don't always look at the same scale, which could also lead to a contradictory result. So looking at the scalar quantities like star formation rate or quenching status is maybe not the easiest to probe the impact of the cosmic wave on galaxy properties. So what we could do is to look at the spin-2 quantity by measuring the intrinsic alignment. And this is what the rest of my talk will be focused on. Okay, when we talk about intrinsic alignment, if you are doing cosmology, you think in general to the pairwise alignment between galaxies, how galaxies point towards each other. And this is super important because this is a contaminant for weakling sync analysis. While this is relatively well constrained, I would say at low redshift, the high redshift behavior of this intrinsic alignment is not super well known. During this talk, I will discuss intrinsic alignment from a slightly different point of view, but I mean, obviously this is driven by the same cause, which is not the alignment of galaxies between themselves, but the alignment of galaxies with their cosmic filaments. And what I will show first is that this is a test to galaxy formation models. And therefore, it is interesting to try to measure this in observation in order to put a constraint on this galaxy formation model. So we very nicely heard from Christophe what drives this intrinsic alignment. So basically, the seed of this intrinsic alignment are imprinted in the initial condition. This is a tidal torque theory, and then matter will galaxy will continue to accrete matter from their environment, which can continue to spin up the proto-halo and later on the halo and the disk galaxies. And in this frame, we could expect this kind of alignment with the filament for the relatively low mass disky galaxies. Then merger could also cause a spin flip along filament, where the orbital momentum of the system is converted into the angular momentum of the remnant here. Yeah, okay, thank you. And we could expect after a merger to see this kind of trend. And additionally, dispersion-dominated galaxies are also expected to be tidal stretched and elongated with respect to their filament. So this was discussed in details theoretically. Now, if we try to measure this in observation, I will discuss this in 2D. So in 2D, we could expect to see this kind of signal. Okay, so disk-like or low-mass galaxies to have this kind of alignment, while early type massive galaxies to have this kind of alignment. I said that intrinsic alignment can be a tool to constrain galaxy formation model. Well, this is because, so what I discuss here is what we expect from theory, but in fact things are much more complicated because gas accretion, merger, feedback, these are highly nonlinear processes which can make this picture more complex. And it's quite interesting to compare the alignment signal between different simulations, which have different subgrid recipes and feedback implementation, which is shown here. So we have 4 simulations. What is measured here is the mean cosine of the angle between the spin and the filament as a function of the stellar mass and you see that depending on the simulation, well, you display at a given mass a different mean cosine, so a different mean alignment. More recently, there was also this nice paper by Sang et al. Where they compare the alignment between spin and shape of galaxies with the different eigenvector of the deformation tensor. And so, for example, if you look here, so this is the direction of the later collapse. So this is more or less the direction of the filament. And you see that horizon AGN in black and TNG have a really, really different signal, and which is an indication that the subgrid physics will have an impact on the intrinsic alignment signal. So observationally, intrinsic alignment was already measured at low redshift in spectroscopic survey mostly. So I have put here some papers which rely on spectroscopic data. What I will discuss today will be more higher redshift survey. In particular, we will work on the cosmos field, which is so not with a spectroscopic sample, but a photometric one, which allows to go at much higher redshift with a higher sampling. But as you see, cosmos is a smaller area than this spectroscopic survey. This work that I will present on cosmos will be complemented soon by James Webb data on the cosmos field, which will provide very much nicer galaxy shape, morphology, orientation, angle measurement. And this is in preparation for the Euclid survey. So Euclid satellite will be launched, as you know, in July, and we will have a photometric survey not over the full sky, but almost. That being said, the photometric redshift accuracy of the Euclid Y survey will be relatively low. I mean, it's not sub% accuracy in the mass range of interest. But we will have the Euclid D field, where Euclid data will be complemented by very nice HSC and Spitzer data, and on which we will reach similar redshift accuracy than on cosmos field. So how do we reconstruct the cosmic wave from photometric data? So obviously, we work with photometric redshift, so there is a confusion along the line of sight, which means that we cannot make a 3D reconstruction, but we have to work in tomographic 2D slice. And this is just to illustrate that the confusion, the redshift uncertainty strongly depend on redshift. And you see that about redshift 1, it is drastically, above redshift 1, it drastically increases, mostly because the Balmer break is shifted into near infrared, which are broader bands. But anyway, this kind of plot gives us guideline on the slice thickness to consider and up to which redshift we can hope to do this reconstruction. Now, this is a typical slice, 75 megaparsec thick slice, and I have overplotted the galaxies which are likely to belong to this slice given their median redshift. But basically, so these galaxies are only likely to be there, and given their photometric redshift uncertainty, they could or could not be on the slice. So what we do is that we do multiple realization by sampling under the PDF of the redshift of each galaxy. And for each of these realizations, I then reconstruct the filament from the density estimated from the Dolonet tessellation. And you see here different reconstruction. And looking at this, you can see that there are some structures which are really persistent. So, for example, here and here, we have filaments which appear in mostly all the slides, and some which are less well constrained, okay? So this is what we get when we overplot all filaments on top of each other. And you see that here we have a strong filament, here as well, and this is a bit more messier here. We have another problem, which is that we have masks in these surveys, and if I do not account for them, that will create fake voids in my reconstruction. So what I do here is that I just randomly had galaxies on this mask, knowing the mean density of the field. We could do better by making a local estimation of the density to fill the mask, but that will be, this is a work in progress. Now we measure galaxy shape on the images, and by doing a profile fitting, and we relate them to the closest cosmic wave filament, and we measure this angle between filaments and the shape. And here is what we get. Galaxies here are classified in early type and disk-like galaxies based on this morphological classification from the ACS. And it's quite interesting to see that we obtain a non-random signal, and in particular, we have this kind of signal where early type galaxies tend to be elongated in the direction of the filament, where disk-like galaxies are more in this configuration. So this is consistent with other works. At higher redshifts, we don't get much signal. I will not comment on this. Finally, in the few minutes which are left, something also interesting is to look at alignment, specifically near groups. Why do we look near groups? Well, because first, an obvious reason is that filaments are better defined near groups because we have a higher density of galaxy. And on Cosmos, we have also X-ray maps from XMM Newton and Chandra, and groups can be identified from these maps. So this is an example, and this is another example where you see here a filament and the X-ray emission elongated in the direction of this filament. Thank you. And here is the result of galaxy alignment near group. And what I show here is as a function of distance to the group. And very interestingly, what we see is that it seems to shift from a slightly perpendicular alignment to an elongation in the direction of the filaments as we go closer towards group. And this is for disk-like galaxies where the signal is stronger. So this can be fit in a picture where galaxies, as they merge when they fall towards group, they are more likely to merge towards group, while they shift their alignment from perpendicular to elongated. Now, I see that Douglas Scott is in the room, and so I presented this at the meeting in Napoli, at a Euclid meeting in Napoli, and he suggested to me to use another estimator of alignment, which is the projected Rayleigh statistic. So I started to make measurement on this. I just added these slides because I saw that you are here. Basically, this is another test for non-uniform orientation, which can be more statistically powerful, and we just confirm what I have shown. Okay, so I'm almost done. Just saying now that we have GWST data and Cosmos field which are coming. This is a first view on this data. I will not detail the Cosmos Wave program because I don't have time, but basically PI are Jan Kartaltep and Caitlin Casey, and we will cover most of the field with James Webb. So how does it help? Well, in terms of what I have just discussed, this will help to measure morphology of galaxies and orientation in the cosmic web. So here is where we have the first visit of Cosmos by James Webb. These are data that we got in January. And so here we have HSC images, and you see that those galaxy shapes are very well, very convolved with the PSF, which is good, but still large. And this is what we get with the James Webb for the same galaxy. And you see that at redshift 0.7, this galaxy is very well resolved. We see the spiral arms, etc. So this is really amazing. Yeah, and that's my summary. Thank you.
Yes, it was a beautiful talk. I'm very impressed with your work, but I have two comments. Can you go back to the slide in which you showed this morphology-dependent transition of the shape directions? You found the difference in the disk and the early type galaxies.
This one?
Yeah, this one. So from observation data, basically you measure the projected shape,
Yes.
direction of the shape.
Yes.
But the transitions occurs for the case of the spin directions, but not for the shape. And numerical simulations show that. So if you relate it to this spin transition, you have to pick up only those galaxies whose shape directions are very strongly correlated with the spin. But majority of galaxies, the shape direction, this minor axis of inertial moment tensor, are not necessarily strongly correlated with angular momentum.
Yeah.
But I'm not sure whether this transition is the one numerical simulation detected for the case of spins. That's my first comment.
Yeah.
And my second comment is about the conventional picture that the merger drove the spin transitions. Actually, although Chris actually gave a very nice talk about this conditional tidal talk theory, my postdoc and I currently actually you cite the paper in your slides, but we actually investigate correlations between this transition or the transition mass threshold and also the merging epoch. So we actually separate the galaxy group into four subsamples according to their latest merging epoch. And we found that actually it does not depend on the latest merging epoch. If this transition really triggered or caused by merging, then we expected to see strong correlation between this transition or alignment change, tendency change, and the merging epoch. But I will give a talk on this Friday, but surprisingly, we found no correlation.
Okay.
So, it's time for us to think about the role of mergers for the spin transition. Okay, that's my second.
Yeah, thank you for the comment. I'm looking forward to your talk and discussing more with you. Yeah.
Is the question online? Oh, there was a question? Okay.
There's a question.
Hello, thanks. Great talk. Had a question about the way you were sampling the galaxies for reconstructing the filamentary structures. I would think that if you're kind of just uniformly sampling them, you would kind of end up with these, wherever there's like a big cluster, you would end up with kind of an extended filamentary structure along the line of sight. If you're just kind of randomly sampling the PDFs of those photo Z distributions of those galaxies. Does that happen, and does it affect the results you're showing here?
So I'm not sure I understood your comment. So you say that, for example, here where I have a big structure, this will this will appear in all the slides basically because there are a lot of galaxies there, and whatever the realization of the sampling, basically I always recover this group. But then you discuss filament along the line of sight, which I'm not sure to...
Or you could just say the group itself will appear artificially in all these slices.
Right. Yeah, sure. Yeah, it will appear in all these slices, that's right. But I'm not sure this is artificial.
Well, I would think, say redshift 2, these photo Z errors will be of order, 50, 100 megaparsecs, potentially. I guess I don't know exactly which photo Z survey you're looking at here. So then that would be a really extended structure. Like, I would say that would be artificially extended.
Okay. But okay, so I'm not working at that high redshift, is mostly up to redshift 1.5, and I'm considering a slice thickness which really encompasses twice the typical uncertainty on photometric redshift and uncertainty. So yeah, I don't think that what you mentioned can be a problem, but yeah, we can discuss it more if
Okay, Chai and then Corentin. Several microphones.
Thank you. Thanks for the interesting summary. I'm curious about the main result where you show in the intermediate redshift range, there is a signal, this one, between the early time and the late time galaxies when we do the split. I wonder if are you ready to put a theory prediction as Christoph has presented on top of this data point to see to what extent they agree?
That would be great, yeah. Maybe I should try to do that. Yes, but I think this fit well. I think the elongation of early type galaxies along filaments is quite, understandable from the theory, and then these galaxies, if we are in the picture, there was this comment first earlier, but if this alignment, the shape is a proxy for the direction of the spin, that will mean that these galaxies tend to have their spin aligned with filaments, which is also what we expect from the theory up to a certain mass. So, there is no the mass transition here from this plot, but not sure we could see it from the shape as we heard before. So I think it fits in the theoretical picture. Now this is just qualitatively an hand-waving description. More quantitatively, this should be looked at. Yeah.
And also on top of that, are we expecting the red data point should be closer to your groups?
Yes, that's a very good point. I had this comment before also when presenting this talk. Actually, here I exclude the galaxies which are close to a group of I don't exactly remember, but I think it's 10 times the visual radius of the group. So I don't seem to be contaminated by groups on this plot. But this is a very good point.
Right. Thanks.
Yeah, thank you very much for the talk. And I'm a strong believer of the cosmic web, but if I was to play the devil's advocate, here you're looking at effects that are relatively small, and you rightly pointed at the beginning of representation that, for example, the stellar mass-halo mass relation is pretty constrained in simulations. So if you only believe in feedback, then looking at that is like the next step after we fix the stellar mass-halo mass relation, for example. So why should people outside of this room care about the cosmic web in that sense?
I'm not sure I understand your point.
Well, it's correction on top of models that are poorly constrained.
Alignment is really an effect of cosmic web on galaxies. So, I cannot create. So if I don't see your point, because if galaxies are randomly aligned, I cannot create this signal. Actually, this is the gray area.
I guess my question is can you constrain, for example, the feedback and star formation models better with that kind of signal compared to fitting
well, then I should compare with simulation with different feedback recipes. And as I showed in the beginning, that depending on the simulation, we can get very different alignment signal. Then overputting them on this could say, well, this simulation is more likely than the other. This is just an additional constraint amongst many, but.
And also you skipped one slide where you're showing like the alignment at higher redshift.
Yeah.
And you said you are not going to comment on it.
Yeah, because I didn't have time. So the redshift bins are overlapping. Okay, here we go up to 0.8 and here we start from 0.5. Okay, there is no signal here. It's difficult to say if it is a redshift evolution or if it is an observational effect, like things are less well measured at higher redshift and then there is no signal. So yeah, I cannot say what happens at higher redshift. Also, yeah, my field is very small, so hopefully with the Euclid deep field, we can put stronger constraint. Thank you.
I think that it's time for break. Let's